In today's new lesson, we are investigating the concept of a limiting reagent and an excess reagent. The term reagent is often used in place of the term reactant, but they are used interchangeably when referring to the initial ingredients, those starting materials of a balanced chemical equation. Whenever I run a recipe, a balanced equation, other than the perfectly balanced stoichiometric ratio, I set up the two terms limiting and excess reagents. Let's just take an everyday example. Suppose a recipe calls for 2 slices of bread plus 1 piece of ham, looks a lot like the bread, maybe even a slice of cheese to equal 1 sandwich. I have 2 slices of bread, a slice of ham, some cheese to create 1 sandwich. All right, so each one of these ingredients necessary in just the right ratio to create what I would call my ideal sandwich. If I were to run any of these experiments with other than this perfect recipe, I set up the two terms limiting and excess reagents. Let's suppose, for instance, instead of 2 slices of bread, I take out 4 slices of bread, doubling the quantity, but I limit the amount of ham and cheese. The bread would be in excess amounts. Heck, I could even place another piece of ham on the table, but as long as I keep the cheese in the same quantity, I cannot follow my recipe exactly to make my ideal sandwich. The cheese becomes a limiting reagent. The same concept is true for any of our ordinary examples. If I wanted to make a 4-legged table, I need 4 legs for every tabletop. Otherwise, I will create an unsteady table. I can't have any other ratio or I have a limiting quantity. That's the same idea in chemistry. The term limiting reagent we'll define into our note pack is that reagent, remember if you don't like that word, substitute the word reactant. It's the initial starting materials that limits or determines the amount of product that can be formed in a reaction. It runs out first. The limiting reagent limits or stops the production of the desired quantity of product that can be formed in a reaction. In contrast, if one of the reagents runs out, we must have excess amounts. It's the one that we have extra of. We put too much quantity, so we have some left over, unused at the end of our experiment. Oftentimes a chemist will run a limiting and excess reagent quantity on purpose just to ensure that the limiting reagent is 100% consumed in a reaction and the excess reagent can be easily washed out of the desired product. We often did this in the chemistry lab. I remember the last experiment we ran, we started with sodium hydrogen carbonate, which was baking soda, NaHCO3, and we limited the amount of reactant we started with. We started with 3 grams of our NaHCO3. I don't know, I have a delay. And we poured in excess amounts of hydrochloric acid. All it would matter is if I made sure that my 3 grams of baking soda was completely consumed, I can pour on all the excess acid I need to, because at the end, if you recall, we dried it over a flame. When we made our sodium chloride, NaCl, we made bubbles of carbon dioxide, and we made water. And at the end of our experiment, what we were able to do is just simply boil any of the water away and the excess HCl. What was completely consumed was sodium bicarbonate, and therefore it limited the amount of sodium chloride we would make in a reaction. Limiting reagent limits or determines the amount of product that can be formed, What we have extra of, poured in excess amounts, is known as the excess reagent. You'll often see me use limiting reagent and excess reagent as my symbols. Let's go to work and represent this with the familiar equation, the production of ammonia. Write the equation for the production of ammonia. 1 molecule of gaseous nitrogen reacts with 3 gaseous molecules of molecular hydrogen, forming 2 molecular molecules of ammonia, NH3. This, of course, is the most efficient recipe a chemist can follow, a 1 to 3 to 2. If I were to run this equation with the perfect recipe, always putting in 3 times the number of moles of hydrogen as compared to nitrogen, I would not have a limiting reagent. I would not have an excess reagent. They would be consumed with that perfect 1 to 3 ratio. It's if I run the recipe by any other ratio that I set up the 2 terms, limiting and excess. For instance, what if I were to run this equation using 2 moles of nitrogen and 3 moles of hydrogen? I double the number of nitrogen but I kept the hydrogen at the same value. Boy, that's just not working well. Let me erase and make that neater. A 2 mole nitrogen versus a 3 mole of hydrogen. So what we have, kind of looking back at the original recipe, instead of a 1 to 3, I run it at a 2 to 3. Is that really going to change the amount of product that I make? Well, of course not, because the hydrogen was not changed. It requires 3 moles of hydrogen to produce 2 moles of ammonia. What I've done really is just added an extra mole of nitrogen that would be sitting there unused. So if I look at the quantity of the balanced equation, a 1 mole of nitrogen versus the 3 mole of hydrogen, and we know that in the equation what gets used is a 1 to 3 ratio. What do we have left over? We have 1 mole excess of the nitrogen, and all of the hydrogen has been consumed. So what we're looking at here is doubling the nitrogen absolutely did nothing to increase the production of ammonia, because what was limiting is the amount of hydrogen. The hydrogen is the limiting reagent, and I'll just label that as LR, the limiting reagent. The nitrogen was in excess amounts to the tune of 1 extra mole of nitrogen. The hydrogen ran out and limited the quantity of ammonia. The maximum yield we could still achieve would be the 2 moles of ammonia from our perfectly balanced equation. And that's true no matter what I do. If I increase the amount of nitrogen but never change the amount of hydrogen, I'll never increase the amount of ammonia that was yielded. Suppose we have a sodium chloride being prepared by the reaction of sodium with chlorine. Let me just extend the page and we'll write this together. So our next example problem. If the elemental form of sodium, Na, reacts with the elemental form of chlorine, which is diatomic, Cl2, we would create a formula unit, an ionic salt called sodium chloride, NaCl. And when we balance that equation, we would notice we'd need a 2 to 1 to 2 ratio. For every 2 moles of sodium, 1 mole of chlorine is required to form 2 moles of sodium chloride, the most perfect, efficient way where I don't have a limiting or excess reagent. It's when I change the recipe ratios that I set up the 2 terms, the limiting and excess reagent. Going on to read, it says, suppose, and this is up here back in your notes, suppose that we have 6.7 moles of sodium reacting with 3.2 moles of chlorine. How many moles of our product, sodium chloride, could be produced? What's the limiting reagent? And we can even solve for how much excess reagent is left over. So under my balanced equation, I always like to tabulate what I'm given and what I want. The first given quantity, I'm just going to put underneath the Na is 6.7 moles of sodium. The next quantity I'm given is the moles of chlorine, and I'll just tabulate that underneath, and I'm going to write that in as 3.2 moles. And what we're being asked to solve for is the maximum yield of sodium chloride I can form, and it asks for that unit in moles. Well, if sodium is our limiting reagent, it would determine the maximum yield, or if chlorine is the limiting reagent, it would be used to determine the maximum yield of our product, sodium chloride. The easiest way to achieve this is just setting up two separate stoichiometric journeys. Let's begin with the first reactant's given quantity, 6.7 moles of sodium. In our heart of the problem, our want over given ratio, I'm going to make that a parenthesis, we see that our want, which is sodium chloride, would have 2 moles of NaCl set over 2 moles of Na. A want over given ratio. It's very difficult to draw with this. Thank you for your patience. The heart of our problem, a want over given ratio. So 2 over 2 times 6.7, of course, gives us the same value. So one option we've just determined with a little mole-mole ratio, 6.7 moles of NaCl would form for every 6.7 moles of sodium we begin with. Well, let's try the other reactant. If I had 3.2 moles of chlorine, what would be the maximum yield of our salt here? So again, we'll set up a nice 1-to-1, a stoichiometric ratio, but here we have 2 moles of sodium chloride for every 1 mole of chlorine consumed. And that here represents our ratio. What's 3.2 times 2 over 1? Well, of course, we're just doubling it. So 6.4 yields. And now we have a decision to make. There we go. So here we're making a choice. 6.7 moles of sodium would yield 6.7 moles of sodium chloride. 3.2 moles of chlorine would produce only 6.4 moles of sodium chloride. Clearly you see the maximum yield of salt must be the smaller of those two answers. So what I do is just compare my answers and find the smaller of the two and label that my maximum yield. I can only make as much as the smaller of my two answers. Therefore, chlorine is labeled as the limiting reagent. It ran out first and determined the maximum yield of product. Chlorine is the limiting reagent. Therefore, sodium must have been in excess amounts, the excess amount of sodium. Chlorine gave us the smaller of our two answers. The maximum yield of sodium chloride would be 6.4 moles. Well, how many moles of excess reagent were sitting there wasted? Of the 6.7, what did we really consume? So my goal here is to begin showing you a journey. Always start the math from the limiting reagent. So once we determined the limiting reagent was chlorine, let's find how much of the other reactant was consumed during the course of this yield. Starting with the 3.2, we now see our want over given. We want to know the excess reagent from the limiting reagent. And so here I'm going to place the stoichiometric ratio of 2 moles of sodium for every 1 mole of chlorine. And these are nice, easy ratios, aren't they? So 2 over 1 times 3.2 we solved for a moment ago. We see that was 6.4. This is the number that was used up of chlorine. That's in a mole unit. Let me be clear with my unit. 6.4 moles of the chlorine was consumed. Well, how much did we start with? We actually started with 6.7. And so if we began with 6.7, used 6.4, that left us a remainder of 0.3 moles excess reagent wasted, unused, sitting in the bottom. Here's what we've just done a first time. We were given 2 quantities of our reactants, and we used 2 separate stoichiometry journeys to solve for the desired quantity of product. We realized that our maximum yield, the most I could ever make, would be the smaller of my 2 answers. I can only make as much product as the smaller of the 2 values. Therefore, I labeled my maximum yield of sodium chloride as 6.4 moles. To determine how much excess was actually wasted, how much of it was not yet used in this course of reaction, we started from the limiting reagent and we went to the excess reagent. Want over given, I want over given, I want to know the excess that was used starting from the limiting reagent. I just compared the initial given, minused out what was consumed, and now I know how much was left over. Oh, this journey will be traveled so many different times. It's worth starting with an easy example. We can clearly see we've labeled the limiting reagent of chlorine because we do not have enough to completely react all of the sodium, and the maximum yield was found. Here's a next example. Write the equation for the complete combustion of ethene. Well, let's begin with that, shall we? A complete combustion pattern. Ethene is given to us as C2H4. If ethene completely combusts, we know to add oxygen. Out comes carbon dioxide and water. Boy, that's frustrating. Let me try that again. H2O there. Thank you. Let's see if I can't get this baby to balance. We've got 2 C's, so I'll start just like you. I'll double the C's here. H's come next, and so I'll start over here. I'm going to double my H's. 4 H's, 4 H's, 2 C's, 2 C's. Now let's take care of the O's. 2 times 2 is 4, plus 2 more is 6, so I can balance that with a 3. A 1 to 3 to 2 to 2 ratio. Daisy. Now let's tabulate what we're given and what we're trying to solve for. We have 2.7 moles of ethene, so I'm going to just tabulate that as part of my given. I'm given 2.7 moles of ethene, and I'm going to react that with 6.3 moles of oxygen. We're being asked underneath, my desired quantity is what's the maximum yield of water produced, what's the limiting reagent, and let's also solve for the excess reagent. How much was left unused? So here I have a 1 to 3 makes 2. What I'd like to do is to know how much water could I maximally form. So I'm going to begin with my first reactant for no other reason than it's written first, and I'm going to start with its given quantity, 2.7 moles of C2H4. And I'm going to make water my target. So my stoichiometric ratio, I see that I form 2 moles of water for every 1 mole of ethene. There is such a delay. There we go, of C2H4. So let's hit 1 over given times 2.7. 2.7 doubled is 5.4 moles. If the first reactant is my limiting reagent, 5.4 moles of water would be my maximum yield. Let's compare that with the second beginning ingredient, a separate stoichiometric journey. Begin with its given quantity of 6.3 moles of oxygen. Go to the same target. We want to compare those two answers. This stoichiometric ratio of water looks like 2 moles of water for every 3 moles of oxygen. I have 6.3, oops, clear my screen, 6.3 times 2 divide by 3 times 2 over 3. I did that twice. Sorry, I got 4.2 moles. Did you get the same when you hit it? So, thinking this through, we're being asked the following. Let's try and make it, there. Compare your two answers. What is the maximum yield of water? It's always coming from the smaller of your two final answers. The maximum yield of our product, which is water, that was our target, was 4.2 moles, telling us that the limiting reagent, the one that was completely consumed, that there's 0 moles left, must have been the oxygen. The limiting reagent is the reactant that gets completely consumed and thus stops the yield of a product. A limiting reagent is oxygen. It was gone, stopping the yield, the smaller of our two answers. So how much excess remains unused? Well, I clearly see that the excess reagent was the initial ethene, C2H4. What we'd like to know is, of the 2.7 moles we started with, how much was used so I can see how much was left remaining. So the next journey starts with the limiting reagent. Always. Everything's determined by the limiting reagent. So I'm going to begin by writing 6.3 moles of oxygen. But this time, instead of the product as my target, my new target becomes the becomes the excess reagent. There we go. So the heart of my problem wants to compare the excess reagent from the limiting reagent. Make the given your limiting and make your want the excess. And I want to just go to a like unit so I can do some subtracting to see how much was actually left over. There, I got it. So what is that stoichiometric ratio? I need that recipe. Every 1 mole of our excess that was consumed, 1 mole of C2H4, used up 3 moles of oxygen. So my stoichiometric ratio is 1 over 3. What's 1/3 of 6.3? When I hit that, I found that would be 2.1. Not done yet. That was how much was used during the course of the reaction. How much did you actually put into this little recipe? Well, you started with 2.7. We didn't use it all, did we? If we began with 2.7 moles, I'm always just stressing that I have to subtract like units here. So if I began with 2.7 and I consumed 2.1 of it, how much was left? And that's right, 0.6 moles left over, unused, of C2H4. That's the excess amounts. And that's what I'll highlight very clearly here. The excess reagent, excess reagent C2H4, it says excess, was left unused. Maximum yield, 4.2 moles of water. Therefore, oxygen, at the end there's none. There's 0 moles of oxygen. It's gone, limiting the product. So all 6.3 moles of oxygen were used, called the limiting reagent. We started with 2.7 moles, but the very definition of excess means that's more than we used. We left 0.6 moles sitting there unused at the end of our equation. We're getting the hang of this. Good work. Let's consider a next equation, and I think we have to flip a page. The incomplete combustion of ethene. This will probably force a different mole ratio, so let's take a peek. Ethene, but undergoing incomplete combustion. So let's take C2H4, C2H4, I had to go back and look. Incompletely combusts, give me, add oxygen. Now this time we stop at CO plus H2O. A hunter can end up doubling because of that odd number, but let's take a peek. 2 C's, there I doubled. 4 H's, 4 H's. 1, 2, 3, 4. So this becomes a 2. Last time we had a 1, 3, 2, 2. Looks like we have half the oxygen. So we have 2 units of O2 giving 2 COs and 2 waters. A 1, 2, 2, 2. If we are starting with 2.7 moles, I just like to tabulate underneath, 2.7 moles of ethene, and the other given quantity was 6.3 moles of oxygen. Calculate the moles of water produced. We call that our maximum yield. What's the most water we can use or we can make? And it asks for a mole unit. Find the limiting reagent, find the excess reagent, how much was left unused. So it's kind of the same story, but now we have a different journey just because the coefficients have changed. Make 2 separate stoichiometric journeys, starting from each reactant and going to the desired quantity you're solving for. So 2.7 moles of ethene, C2H4, begins. I'll have a want over given ratio, and I want to get to moles of water. So this ratio looks like every 2 moles of our product water, that says mole, we have 1 mole of the reactant ethene. 1 mole C2H4. And what does that come out to be? 2.7 times 2 we hit was 5.4. That looks like an 8. There, I got it. 5.4 moles, one possible answer. Do a separate journey. Suppose we started with 6.3 moles of oxygen. We have a different ratio now because we have a different comparison. We have a 2 mole of water target. Oops, I lost my pen. There we go. 2 mole of water target. For every 2 moles of oxygen consumed, Reactants get used, products get made, so oxygen is indeed being consumed. And 2 over 2 times 6.3 is 6.3. What is our maximum amount of water we could possibly make with those ratios? Well, of course, we're looking for the smaller of our two answers. Comparing these two, 5.4 is the smaller number, so the maximum yield is 5.4 moles of water. And I'm going to label that. Do that with me. Get in the habit of labeling your maximum yield. I can't know, just if you're not indicating over here on the product side what you believe to be the maximum yield, I'll never know if you know the answer. So make sure you label that. And now all of a sudden here, the C2H4 became the limiting reagent. Therefore, the molecular oxygen must have been in excess amounts. Limiting reagent, C2H4, the excess reagent, the oxygen. Reagents are reactants, they're the left side starting materials. The products get made, so the maximum yield of water, 5.4. Well, of the 6.3, some of that mole of oxygen left sitting there unused. Let's calculate how much would be unused. And again, start your problem from your limiting reagent, which is the C2H4 in this case. Limiting reagent. But now make your target, not a product, but make your target the other reactant. Oh, that's not very neat. So my want over given, I want to know the excess reagent. Its coefficient was a 2. For every 2 moles of oxygen, 1 mole of your ethene got consumed, so that 2-to-1 ratio. And so here we have 2.7 times 2. We've just done that math up there. We said 5.4 moles. But this label is of oxygen was used. How much did we start with? Well, we began with the initial amount of 6.3 moles. And what difference there is between what you started with and what was actually consumed to produce product gives us the remainder left over sitting there unused. So 6.3 minus 5.4, and that comes out to be 0.9 moles. So 0.9 moles of oxygen were in excess amounts at the end sitting there unconsumed, just as you had placed them in. Let's expand the borders. We've been doing a lot of mass problems, and those are great, mole problems, and those are great to get the hang of what we're doing, finding maximum yield, determining limiting and excess reagent. But we know that moles are the least common way that we actually measure matter in a laboratory setting. Whatever measurement we make in terms of weighing, volume, or particle number, we always convert back to the mole. So this is probably a more realistic example because we're going to do a mass. If copper reacts with sulfur, solid copper 1 sulfide is formed. Let's begin with that balanced equation. I'm going to give myself room down here. So here I have solid copper. I'll just write that as Cu. Reacting with sulfur, forming copper 1 sulfide. Copper with a +1. Sulfide would be a -2, so we get a compound Cu2S. So our balanced equation, 2 to 1 makes 1. Combination. When a metal hooks to a nonmetal, they hook by charge. Let's tabulate what we're given in terms of information. What is the limiting reagent if I have 80 grams of copper reacting with 25 grams of sulfur? And I'm going to keep reading because I like to know. We're going to be asked, what's the maximum number of grams of product that can be formed? So we want to know the maximum yield of the product. Once we determine the limiting reagent, we'll always be asked to determine how much excess reagent was left over, unconsumed, unreacted. So here we have the same idea. Two separate information pieces are given to us, but the same quantity over here. So we have two separate journeys. Once we do two separate mass-mass problems, we're just going to find the smaller of our two answers. So for instance, if the 80 grams of copper limits the equation, it would give us the maximum yield. To move all the way from the left to the right, I know it's a three-step stoichiometry journey. I just like to get my three parentheses ready so I can see my target. By the time I'm done going through my converting process, I'm going to be at the grams of Cu2S. There's my target. Where the heart of my problem is my want over given ratio. Let's get the next journey just set up, and we'll go through and set up those parentheses. Suppose 25 grams of sulfur were my limiting reagent. It then would provide for me a three-step journey to find want over given, where we still have the same target, the Cu2S. We need some mole map work, don't we? To convert grams of copper to moles of copper, we need the molar mass of copper. Finding from your periodic table the mass of 1 mole of copper, 63.5 grams. It's gram atomic mass. 1 mole of copper would weigh exactly 63.5 grams of copper. We want over given my mole ratio. Remember, we want the product, Cu2S, so its coefficient goes on top. 1 mole of Cu2S requires 2 moles of copper. So my stoichiometric ratio, a 1 over 2. I have to do a molar mass for Cu2S, 63.5 times 2 for the 2 coppers, plus 32 for the sulfur, and I get a molar mass of 159 grams. The mass of 1 mole of Cu2S. Let's hit that, shall we? I'm starting with 80 grams of copper, 80, divide by the molar mass of 63.5, times 1 over 2, times 159, the molar mass of Cu2S. And I came out with 100.16, we'll say. One possible choice so far. If 80 grams limits the amount of product, here would be my maximum yield. But I'm not sure yet. I have a second journey to take. So let's get going there. We've got 1 mole of sulfur set over its gram molecular weight of 32, gram atomic weight of 32. So 1 mole over 32 grams converts 25 grams of sulfur into a mole. The heart of my problem compares the stoichiometric ratio. I see that 1 mole of Cu2S is produced for every 1 mole of sulfur put in. A 1-to-1 stoichiometric ratio. We have the same molar mass, so that's handy. We already calculated it. 159 is the molar mass of Cu2S set over 1 mole of Cu2S. And let's hit there. So we'll take 25, divide by 32, times 1 over 1, I won't bother hitting, but times 159 I'll enter in, and I see that answer is 124.2. 0.21, so I'll just do 0.2. Compare those two. These are your product. What is the maximum yield of product? Well, obviously it's the smaller of your two answers. the maximum yield is the smaller of my two calculated answers. Maximum yield of product is 100.16 grams. And therefore, copper must have been the limiting reagent. Even though it weighed more, it actually got consumed, leaving excess amounts of sulfur. If copper is the limiting, that makes sulfur the excess reagent. Remember, reagents, another word is reactant. So if I label copper as the limiting, sulfur must be in excess amounts. Well, how much of that 25 grams we started with didn't get used? How much was extra in the recipe? To determine that, we do another stoichiometry problem. It's the third one, I know, but it's required to find. If I started with my limiting reagent, and this is what I'm beginning with, all math is determined by the limiting reagent, I'm going to set up a new journey that doesn't target a product like up above, it targets the other reactant, the excess reactant, which was sulfur. I want to go to a like unit so I can subtract. So that's why I'm getting this ready. I want to see my target. What I'm about to calculate is the excess reagent that was consumed, or in other words, used to make the product. I can then compare it to the 25 grams I actually started with. So let's go to work. We have step 1. I got to convert my grams of copper to moles of copper, and it has a molar mass of 63.5 grams. In the heart of my problem, there, I got it. In the heart of my problem, I want the excess from the limiting. I want to know 1 mole of sulfur from 2 moles of copper. In the last step, let's use the molar mass of sulfur to get out to a gram unit, just so I can subtract like units. Since the quantity was given to me in a gram, I better end in a gram so I'm able to subtract. I'm going to start with my limiting and I work to the excess. 80 divided by 63.5 times 1 divided by 2, 1/2, times 32, and I found a value of 20.157. Shall we say that's 20.16? Shall we round a little bit? Used. Okay, we're not done. We want to know how much was left over, unused. So remember this, we started with 25 grams. That was the given quantity. So with 25 grams, the initial amount of the 25, I used 20.16. What's the difference between the two? Well, that would leave me 4.84 grams of sulfur in excess amounts. We put in 4.84 grams of sulfur extra when we ran this recipe. There is no limiting reagent. The definition says it's gone. When it runs out, I stop the production. I can only make 100.16 grams of product because now the copper is gone. Of the 25 grams of the other reactant I started with, the reaction consumed 20.16 grams of it, leaving me an extra amount of 4.84 grams of sulfur. That's a good one. Lots to think about when we do limiting and excess reagents. We have one more in our note pack. Hydrogen gas can be produced in the lab by the reaction of magnesium metal with hydrochloric acid. Oh, we've done this experiment many times. Let's write the complete balanced equation and define the limiting reagent given the following quantities and determining how much hydrogen can be consumed. So let's extend the page and start with a nice balanced equation. Magnesium metal is going to react with hydrochloric acid. You recognize the pattern of chemical change? It's called a single displacement reaction. Magnesium reacts with HCl. You see the magnesium kicking out the hydrogen? They exchange places. So molecular hydrogen gas forms, and the other product would be magnesium combining with the chloride, and based on charge, we know Mg is a +2, Cl is a -1, so we get MgCl2. And then we balance by doubling the HCl. Solid magnesium, aqueous acid, gaseous hydrogen, and aqueous magnesium chloride. Now let's tabulate the numbers given to us, and I just do so right underneath the ingredients. It gave us 6 grams of HCl. I'm just putting that right under there. Whoops, I don't even need to write of what. 6 grams of HCl. And the other number was 5 grams of magnesium. My target, kind of reading through the whole story problem, my maximum yield to be determined is that of hydrogen, so that's my target. We'll be asked to identify the limiting reagent, the excess reagent, and the maximum yield of hydrogen. We're getting good at these. We have 2 separate mass-mass problems to compare to find the smaller of the 2. If indeed magnesium is the limiting reagent, it would be provided to us as a 3-step journey with a mass-mass target of hydrogen. I'll get those parentheses ready so we can see the target at the end of the journey. We're going to divide, ratio, multiply. Let that catch up. There we go. I don't know why it's doing that today. Let's get the other one ready. 6 grams of HCl. Again, a 3-step journey, so get those ready with me. Divide, ratio, multiply. Same target, grams of hydrogen. There. All right, so here we go to work. 1 mole of magnesium set over its atomic weight of 24.3 grams. Grab that right off your periodic table if you don't have it kind of just known by now. To convert moles here, we need the molar mass. So 1 mole would weigh 24.3 grams. Look at our ratio. We have a 1-to-1 stoichiometric ratio. For every 1 mole of hydrogen, you have 1 mole of magnesium. And of course, the molecular weight of H2 is 2 grams per mole. Let's hit that, shall we? Got my math set up. We have 5 grams. I'm going to divide by the molar mass of 24.3 times 1 over 1. I don't bother hitting, but I go times 2, the molar mass of hydrogen. And one possible answer is 0.4115, so we'll go 0.41 grams of H2. Let's see what the next journey would give us. Here we're going to convert moles into moles of HCl, so its molecular mass, 1 for the hydrogen, 35.5 on the chlorine, so that's 36.5 grams per mole for HCl. Same target. I want to know hydrogen. Its coefficient is a 1, so I place 1 mole of hydrogen on the top. Coefficient for HCl, however, is a 2, so my ratio here is 1 over 2. I still have the same target, the molar mass of molecular hydrogen, 2 grams per mole. There, I got it. So let's hit 6 divided by 36.5 times 1 over 2 times 2. 2 grams of H2. And here's my next answer, 0.164. I'll just 0.16. 2 decimals are fine. So what have we determined? Comparing these two values, HCl determined the smaller of the two, so the maximum amount of product that I could make, I'm going to label that my maximum yield, is 0.16 grams. The maximum yield is determined from the limiting reagent. Therefore, the magnesium must have been in extra quantity, the excess reagent. HCl limited the amount of product formed. Of the 5 grams of magnesium, not all of that got used. Let's determine how much magnesium remains unused. Always, always start your next problem from the limiting. We're not going to the product this time. Start from the limiting and go to the excess reagent. 3-step journey again. We just have a lot of math in these types of problems, but it's simple math, and you're getting the hang of it. You're getting good at this. We're going to divide, we'll ratio, we'll multiply, where the target now becomes the excess reagent, and I want to land in a like unit that I was given so I can subtract. And that like unit here was in a gram. 5 grams of Mg, so I'm going to go to a gram. I want to know, of the 5 grams I've started with, how much was actually used so I can determine the extra quantity. So the 5 is an extra amount. Let's determine how much of it was consumed through the course of the reaction and then subtract to find the remainder. So starting from the limiting, we go to work with some mole map work. 1 mole of HCl, we already determined here, has a molar mass of 36.5 grams. Our want over given, 1 mole of magnesium requires 2 moles of HCl. No sense hurrying it, right? I get messed up. 2 moles of HCl. Alrighty, and now we want to go to grams, so we use the molar mass of magnesium, our target, which was 24.3. That's its atomic weight right off the chart. So here I have 6 grams, it says Mg, 6 grams of HCl, I'm going to hit that in, 6, divided by 36.5 times 1 over 2 times 24.3, and I found 1.997. 1.997 is pretty darn close to 2. What do we want to do? Round a little bit. 1.997 on my calculator I'll put in as 2 grams. Therefore I can make this subtraction easy. We put in 3 extra grams of magnesium metal. The excess amounts unused in excess quantities. I'm trying to make that an S. We've done so much good work in determining the limiting reagent, the excess reagent, and the maximum yield. This particular section called Limiting and Excess Reagents, very involved math, but the math is repetitive. The more we practice, the more proficient we become. Good work today.